Okay, good morning all. Many thanks to the organizers for organizing this very nice program and giving the opportunity to speak. So today I would like to talk about a project on the path integral derivations of K-Theoretic Donaldson invariants. And so let me just start by setting the stage a little bit. These Donaldson invariants, they are invariants of four manifolds. So let X be a smooth, compact for a manifold. And then we consider a field strength F. For some Lie algebra G as the curvature of some principal bundle P. Curvature of a principal bundle P, and then there is a set of well-studied spaces, the instanton moduli spaces. Actually, let me write it on this board. I don't want to make it too small. So these are spaces M sub K, are the spaces where the curvature self-dual part vanishes. And these are for instanton number K, where K is then minus 1 over 8 pi squared times the integral of trace FHF. Okay. And in this talk, I will pretty much for the whole talk restrict to G is SU2. Okay. And so there is already for over 40 years, I think now, interesting relations between these intersection theory on these moduli spaces and the classification of four manifolds. So topological invariance of X and intersection theory on MK. Okay. And in particular, it can kind of distinguish between differential structures of the four manifolds. Okay. Any questions? Okay. Okay. So let's go back to the work by Witten on the late 80s. We can understand this in terms of path integrals of topologically twisted Young-Mills theories. So path integral let me call it perspective or derivation using topologically twisted theories. And different topological theories will give us different differential forms to integrate over these moduli spaces. So, for example, the pure n equals 2 SU2 theory gives these so-called Donaldson classes. If you consider n equals 4 theory, you get the Euler character of the moduli spaces. If you consider adding hypermultiplets in the fundamental representation, you get so-called Segre classes integrated over these moduli spaces. And today I want to discuss K-Theoretic invariants. And this is a project with Hyun Kim and Greg Moore and Runkai Tao and Xinyu Zheng. And hopefully appear not too long from now. Okay. So what are these K-theoretic invariants? Let me say a little bit more about them. We saw them also yesterday in the talk by Taro. To this, let me specialize to space, more general space M, not necessarily a moduli space of instanton at the moment. Be a spin manifold. So I do require that it is a spin manifold. And then we can consider the index of the Dirac operator, which is basically the K-theoretic invariant of the title of the talk. So we can consider the index of the Dirac operator. And in terms of index theory, this is the integral of the A hat genus of the tangent bundle of the manifold. Okay. And we'll find an integer. Okay. If the manifold is not spin, you can still do this integral. Then typically you will find a non-integral value, but then you cannot properly define these Dirac operators. Now in algebraic, for this project, we are inspired by work by algebraic geometers who usually work with a slightly different index density. So mathematicians often consider the tot class integral over the tot class of M that's related to the A hat genus by the exponent of the first Jernkles of the tangent bundle divided by 2. Okay, and this is always an integer, also if M is not necessarily spin, and it is a so-called holomorphic Euler character of the manifold. Okay, any questions? So it's the Euler characteristic where we sum over sum over these Hertz numbers of the manifold with alternating sets. Okay. Any questions so far? Okay, we can also couple the Dirac index to a line bundle. So couple maybe couple to a line bundle L such that we get the index let me see with connection A, and then we get this index, which is then related to the first one just by the C1 of L. Okay. questions so far? And you can go between this one and this one if you allow for these half integer churn classes or bundles which are not really well defined. But then somehow the Dirac operator is not the spinners are not properly defined, and then the line bundle will not be properly defined, but their product is properly defined. Okay, so with this review, we can introduce the K-Theoretic Donaldson invariants. Which are nicely combined into a generating function which depends on this curly R, and this line bundle L indicates line bundles over the instanton moduli space. We get a generating function over the instanton numbers and the power series in this curly R, which is for now just a generating variable. And then we get the indices of the Dirac operators over the instanton moduli spaces, where this A is the connection for this line bundle L. Of course, it's for every instanton number, it's a priori a different line bundle because there are different moduli spaces. But I hope this is clear. Okay, any questions? And so this was quite this was studied within algebraic geometry in a paper from 2006 by Götze, Nakajima, and Yoshioka. 2006. And to kind of understand this from the more physical perspective, we will go to a five-dimensional gauge theory. 5D. Maybe I should add N-1 supersymmetric, 5D N-1 gauge theory. On the form manifold X times S1, and the first references were by Losev, Nekrasov, Shatasvili from this one was 97 actually. Then there is a paper by Nekrasov from 96. Yeah, so this is we are integrating over this is the index of the Dirac operator on the moduli spaces of instantons on X. That's the like. R is for now just a generating parameter, but we will connect it soon to the radius of the S1. Other questions? Yes, there's some subtlety, but in the good cases you will reduce to the standard Donaldson variant. And indeed, you can then introduce further Donaldson classes in this integral, which I will not do in this talk. It becomes otherwise the formulas are getting very very long. But you can introduce the usual Donaldson classes, and then if you take the limit R to 0, then you're left with those intersection numbers. Yeah. This will be integrals over MK if you go to this. Yeah. That's right. Other classes. This is, it's for, for algebraic surfaces. They make some comments about more general form manifolds, but it is all the techniques analysis is for algebraic surfaces. So indeed, for these class of surfaces, it's explicit results are feasible in the mathematical literature. For more general form manifolds, this is usually not the case. On the other hand, for these the physical analysis does not require this restriction to algebraic surfaces. So what I will be talking about, you can do for arbitrary smooth compact form manifolds. No, I will say later on a little bit about it. If you consider it, if your manifold X is a toric manifold, then you could include equivariant parameters, and then you can further refine this with epsilons. Sorry. Okay. No other questions? Okay, thank you. Yeah, feel free to interrupt with any questions you may have. Okay, let me then start by reviewing a little bit about the 5D theory we will consider. And this is actually precisely the theory Fabrizio Del Monte was discussing on Monday, which you can geometrically engineer by using a local Calabi-Yau manifold with P1 times P1 as the compact surface. So we have a vector multiplet consisting of the Gates potential, 5-dimensional Gates potential AM, and a real scalar field sigma. And we have the 5D Gates coupling. G5D. And we have the following global symmetries. So we have an SU2R symmetry. Then we have a so-called U1I instanton symmetry, and there's another U1, which is the Klutzer-Klein symmetry. Sorry, this is then for R4 times S. Actually, let me do it this way. I won't talk about the Klutzer-Klein U1. So this U1I comes about because we have in 5 dimensions an additional conserved current, which is the star of the instanton density trace of F wedge F. And so we have this global symmetry, this factor will be quite important for us. We can weakly gauge it by including a frozen vector multiplet for this group. So we get a vector potential AMI and another scalar field sigma I, and we'll set constant background values for these fields. Okay. And there's one thing which will be important is the mixed Chern-Simons term for this U1 instanton symmetry and the dynamical Gates field. And takes the following form 1 over 8 pi squared integral over R5 AI. Sorry, let me, in terms of the field strength, Fi, where it's the standard 3D term ADA plus 2/3 A cubed. Okay, and we can supersymmetrize this term, and one term you will find is the following integral over R5 sigma I, where it's the trace of f wedge star f plus many other terms. So one thing which is intriguing is that here we have the kinetic term of the Gates field. So if we set sigma, we can set sigma I to give to express it in terms of the 5D Gates coupling, and then you can precisely get the standard kinetic terms of the vector multiplet out of this mixed Chern-Simons term. So in some sense, if you set the background values of these U1 I fields appropriately, you don't have to include separately the kinetic terms of the vector multiplet. And the appropriate value is then 8 pi squared over G 5D squared. Okay, any questions? Okay, and these terms also then give us directly a coupling of these fluxes, background fluxes of the global symmetry to the dynamical Gates field. Also coupling to U1I fluxes. Okay, so I didn't, sorry, I should, warning a little bit with the head, but these fluxes with a factor of 2 pi are integer quantized. Okay, any questions? Okay, so that's more or less just the review for flat space. Let us now proceed with a four manifold X times a circle S1. Then we consider a circle of radius S1 has radius straight R. So this is a dimension full radius. It's still different from the curly R I had on the board earlier. We partially topological twist on X with the Donaldson-Witten twist, making use of the SU2R part of the global symmetry group. And then we get a complex scalar on, if we view the theory on X by adding the holonomy of the gauge field of the U1I gauge field to the real scalar. So we get sigma plus I over R integral over S1 A I dx dxm. Okay. And so we can choose a gauge where this is then in the is diagonal of the usual Seiberg-Witten form. Oh, these M are the indices of the gauge field running from 1 to 5. You can choose a basis where this is just A5 and the component along the S1. Oh yeah. Oh sorry. I have this. No, this is not. Sorry, there's no I. Sorry. Oh, then if we make this choice, then we get the kinetic term, the standard kinetic term of the dynamical gauge field. Yeah. By supersymmetrizing this, starting from this term. And so yeah, there will be many more terms, but yeah, you kind of it includes the standard kinetic Lagrangian of the factor multiplet. No, we consider this as the full action for now. So that's there. Yeah, there's also a five-dimensional Chern-Simons, but we are not considering that now. You would get to a really different theory, and you would calculate different things. Thank you. I think so. Yeah. You don't have to. Okay, I have to go back to the details. Yeah, we do generate it and then set sigma I to this value to get the standard kinetic term, and then we have the coupling to the fluxes. Yeah. I think from this one that this will be included, so you would not only get topological terms if you supersymmetrize this one. But I'll be happy to discuss afterwards. Okay. There are other questions? Sorry, is the sorry, what type of objects? No, I don't think they are defects. These are just kind of external fluxes, so we get an extra coupling in the Lagrangian, and in this way you basically get a full infinite family of theories. So kind of now having gone to x times S1, these will be integral fluxes on. We'll choose them to be integral fluxes on x, and they will induce the line bundles on the moduli spaces. And is that answering? Good. Mm-hmm. Well, we don't. There's not special behavior of A near these surfaces or the Poincare dual of these surfaces, as far as I'm aware. So I wouldn't call them surface defects. But, okay, where? Okay, thanks. So, indeed, this is the SU2 gauge field, and now we to explain this curly R, we have a four-dimensional scale lambda, and then R to the straight R to the 4 times lambda to the 4. We define it as curly R to the 4, which is dimensionless, and this is equal to this expression in terms of the 5D coupling, G5D squared plus I AI integrated over S1. Okay. Okay, so we have a 4D limit where we keep A and lambda fixed and send R to 0. Then this curly R will go to 0. And we have a 5D limit where we send, sorry, there's still an R here, since the G5D is dimension full. There is a 5D limit where this ratio R over G5D squared goes to infinity, and then still this curly R will go to 0. Okay. So in both the 4D limit and the 5D limit, this curly R will actually go to 0. Okay, any questions? Okay, so we can do a reduction to S1. We get a supersymmetric quantum mechanics with target space MK. So you use the collective coordinates. You kind of perturb around one of the BPS solutions of the theory, and so for every instant number k, you get supersymmetric quantum mechanics. So as I said, we calculate the index of the Dirac operator. But now there is one puzzle that the moduli spaces, instant moduli spaces, are not necessarily spin. However, the MK are not necessarily spin, and then we have an anomaly in the quantum mechanics, which we could then change by choosing these fluxes appropriately. Okay. So and there is a topological condition. Topological condition. Cancelling the anomaly, and this is that the second Stifel-Whitney class of the Gates bundle with the inner product of the second Stifel-Whitney class of the four-manifold X plus this flux n I is an even number. Any questions? So there are cases where you have to include this flux to get a well-defined to be able to introduce your spinners on these moduli spaces. Okay. P is the say the Gates bundle on X, or the principal bundle on X. Principal. Okay. Okay, let me then go back to the 4D perspective. And explain a little bit how from the point of view of the four-dimensional theory, we can set up a path integral, and evaluating that path integral, then reproduce these the generating function of these indices. So on the Coulomb-Brands of these theories on x times S1, they are the order parameter is the wave of the Wilson line. Coulomb-Brands. Parameterized by the wave of the Wilson line in the fundamental representation. So we get a trace in the fundamental representation of the path ordered product of the exponent integral over S1 sigma plus I A5 dx5. And this is usually denoted with the capital U as a straightforward generalization of the little u, usually used for the pure four-dimensional theories. And if we expand this, the first terms will look like e to the RA plus e to the minus RA, and then there are further terms which are can be expanded in powers of R to the 4. Okay. This theory has an electric Z2 one-form symmetry. which in the older literature is known as the center symmetry. Um, then So then we have also an anomaly in the 4D case. I will actually say something now, about it because it is related to this one form symmetry. Um, um, so this is basically one way to understand this this symmetry is by doing a Gates transformation, which is not periodic around the S1, but it comes back up to an element, the element of the center, which is just -1 for SU2. Then the the Wilson line just changes by this by the center, so this u will change to minus u. Um, yeah, you would say it's zero form. Okay, yeah, okay, there's, yeah, okay, good. Okay, and there's a Seiberg-Witten solution for these theories, and you can calculate the prepotential. I won't go in too much detail here. One thing to mention is that we have, from the Seiberg-Witten solution, we find the following, you obtain the following relation for u as function of tau, where tau is the effective coupling or the second derivative of the prepotential to A. And this function can be expressed in terms of modular forms, 8 r to the r squared function u of tau. Yeah, go ahead. No, that in that case you cannot, the phase of the fermionic determinants in 4 dimensions, the sign of the determinant of the fermions in 4 dimensions is ambiguous. And as I will explain, you get these two copies, and they have an opposite sign, so the path integral will be 0. Well, that it is, how to say, it's, yeah, the sign of the determinant is not well defined. Let me say it that way.
Is that term that you wrote on the right? Is that the
This way. Yeah. That. Right.
So what happens when this if it's non-zero?
Then the path integral will be 0 because the two copies. Yeah, I think that you can say it that way. That it is you cannot because you cannot define the spinors appropriately. That's another way to say it. Okay, so we get this relation which is invariant under the symmetry. We get the two signs, and this u of tau is a function of the Jacobi theta series. It's not maybe very important at this point, but it's theta 2 to the 4 plus theta 3 to the 4 divided by 2 theta 2 squared theta 3 squared. The u plane has four singularities. U 4, u 3, and u 1, u2. U2 is equal to 2 plus 2 r squared, and u4 is equal to minus 2 r squared, and then this one is plus 2 r squared, and this is 2 minus 2 r squared. And so we get two copies of the usual Seiberg-Witten little u plane. Sorry, now this is gone, but then we have one copy around these two singularities, and we have one copy around these two singularities, and they are precisely exchanged by this Z2 symmetry. Now it has been quite useful to map these capital U planes and little U plane to a domain in tau space for integrating over these U planes. So this is kind of following up from a paper by Closet, Magurinu, and Assmann, Elias, and myself. And this will, in this case, it will look as follows. The modular function written there is a modular function for the so-called gamma not 4, which is the following domain with cusps at 0 and 2. These are these two singularities corresponds to the U1 and U2. Now we get two of these. We get a double cover because of the U squared. We can put them next to each other, which is standard for modular functions. So we put them next to each other, and we have here then 4 and 6 mapping to the other two singularities. And of course, the space is connected, so we have these two spaces talk to each other with a Brand's-Cut. We have a Brand's point here, and then a Brand's cut going up. And the left side of this one is identified with the right side of that side. So the effect is that here, if we are here, then we have a tau to tau plus 4 periodicity, because these sides are identified. And if you are up here, then if you go through here, you end up here. Then you go here, 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 and we have a tau to tau plus 8 periodicity. So that this path kind of goes around all the singularities, and this path just goes around U1 and U2 singularity. Okay. Any questions? It would work on. Oh, this is okay for our 4 times S1. Now, next step will be, we go to x times S1 and set up the U-plane integral. And this is the path integral for the topologically twisted theory on X, which reduces to an integral over the 0 modes. And so then we are just integrating over this domain for the scalar field. So this is for B2 plus is 1, but we can actually then deduce also contribution for B2 plus larger than 1. So let me just sketch a little bit this integral. Mu corresponds to the first Chern class of the hoofdflux of the gauge bundle. It's a function of R, and we get an integral over this fundamental domain. Fr, and it has some kernel nu of tau over u is how it comes out, times a sum over u1 fluxes tau bar and v bar. This is a coupling d second f dai, and actually let me, there's a c to the n squared, another coupling to this. This is the Ni flux to the background flux. Okay. And for the 4D case, we are instructed to make first a small R expansion, and then we integrate over basically two copies below the branch point. The branch point move up in that limit. And the integral over each copy has the same magnitude, but it differs by a sign, well, potentially by a sign determined whether the moduli spaces are spin or not. Okay, I have to speed up a little bit. So how it comes out is something of the following form: 2 times 1 plus minus 1 to the power 2 mu dot kx, or I wrote earlier w2 of x plus this flux n, and then you pick up the the zeroth coefficient in the Q series after making expansion in small r of nu of tau over u c n squared and a mock modular form which is used to integrate this sum over fluxes. Okay. So at the end of the day, if let us just look at an example, we can take x is P2, or actually from the physics perspective, any four manifold with B2 plus is 1 and B2 minus is 0. Then if we take a half integer choice for mu, it looks as follows. It is 1 for n is plus or minus 1. 1 plus r to the 4 plus other terms, n is plus or minus 3. 1 plus, I think, 6. R to the 4, n is plus or minus 5, and 0 for n even. Okay, and so this confirms then explicit results by Gutsunaka, Jima, Yoshioka in their paper from 2006. And you can also kind of run this game for a bit more complicated manifolds like the Hitchable surfaces, etc., or take this mu equal to 0, but then there is no anomaly. All manifolds are all spin. All moduli spaces of instantons are spin. So this is always equal to adds up to 2. Yeah, mu is it is the class of the trace of the dynamical gauge field. No, sorry. So, right. F SU2 is F over 2. Okay, so the non-abelian gauge field splits into, in the low energy theory, there's a U1 unbroken, so we have this dynamical U1 gauge field F, and then mu is equal to the class of F over 2 pi. So it's the first Chern class of this line bundle, but it is half integer. It comes out as half integer because of this factor of 2. H2 x. We need to double check whether this 2 is a 4, but okay, that's basically that's it. Okay. Other questions? No, I've maybe 2 minutes if that's okay. Sorry? Which this one? Yeah. Yeah. Then these indeed those integers in front of the r powers of r are the holomorphic Euler characters of instant moduli spaces. Maybe coupled to the line bundle induced by the coupling to the U1I flux. Okay, just to wrap up, you can do another calculation for P2 since it's a toric manifold using toric localization. So it's quite a different calculation. Then you express this flux F in terms of the equivariant classes on the manifold, and it comes out as follows. So we get a partition function which now depends on R and the flux N and epsilon 1 and epsilon 2. It takes the form of some normalization. We get a sum over 3 tuples P corresponding to the fixed points in the installed moduli space. We can let them contribute with some big theta, which is 0 or 1, times some contour integral over the A coordinate and the product of Nekrasov partition functions. I always want to free Z Nekrasov, and you have to choose all the arguments appropriately, so you get AL, epsilon 1L, epsilon 2L, lambda R and NIL. Okay. Okay, and if you do this calculation, you'll find the epsilon refinement of those expressions that are you get power series Laurent. You get power series in R to the 4. With coefficients Laurent polynomials in e to the R epsilon 1 over 4 and and these parameters e to the R epsilon j divided by 4. Okay, so you have to get the epsilon refinement of the result above. Okay. So that brings me to the end of the talk. So we have a rather explicit picture of reproducing these K-theoretic invariants for this specific theory, and yeah, for us as outlook, we are looking at different theories since there's a big yeah, there are many different of these type of 5D theories, which may provide other yeah, interesting aspects. On the one hand, of formulating those theories on these geometries, and on the other hand, in terms of data for four manifolds. Okay. Thank you for your attention. Yeah, I wouldn't say that it's a K-theoretic version of Seiberg-Witten invariance. If we go to B2 plus, so if you look at the Seiberg contribution of Seiberg-Witten invariance, so for P2 the Seiberg-Witten invariants are 0, so they don't play a role. The Seiberg-Witten invariants, they are associated to these singularities in the Coulomb branch moduli space, and the form they take is that you have a sum over these Seiberg-Witten basic classes, then the Seiberg-Witten invariant, and then we get some function which depends on mildly on C, and then depends on R and maybe some other properties. Basically, C only appears in the exponent of these functions. So you get things of this form that you get, say, f of r to c squared, and there might be an a of r to the chi of x, and a b of r to the sigma of x. So the kind of the data about kind of these Dirac indices sits in these functions. This is just the usual Seiberg-Witten invariant, counting the monopole solutions. Of these, so you series expand this whole function, and then you will find something of kind of that form there. That there's a power series in R with integer coefficients who are then the holomorphic Euler characteristics of the moduli spaces. Yes, sir. Yeah, for what I discussed today, it is it's the same information as the Seiberg-Witten invariants and Donaldson invariants. Yeah, in terms of it's basically this picture that this from the U-plane you can derive also the Seiberg-Witten invariants using a bit of an intricate procedure, but it is again determined in terms of the Seiberg-Witten invariant, so it doesn't in that sense give us new information to distinguish four manifolds. That's true. Yeah, we don't have to restrict to algebraic surfaces. Yeah, that's true. So but the Seiberg-Witten invariants are well studied also beyond algebraic surfaces. But indeed, we can say now that physics at least suggests that those coefficients continue to hold for all manifolds with B2 is 1, not just the algebraic, just the surfaces of algebraic type. And that they, sorry, the U-plane compared to? Mm-hmm. Yeah, so the Euler numbers corresponds to n equals 2 star on the physics sides, which we looked at. Segre invariance corresponds to fundamental hypers. We looked at Johannes Assmann and Elias Furr. I guess the next step up with mathematicians have results is elliptic genera. So then we would need to go to a 6D theory. And so, yeah, so that's further down the road. The kind of the standard 6D theory is anomalous, so there needs to be some yeah, that has to be looked at carefully. But for now, we are just we went one dimension higher to 5 dimensions. I think that. Yeah, then there is the case of the refinement. You can refine the holomorphic Euler characters. Instead of -1 to the n, you can have -y to the n. Or for the Euler, in terms of rather than looking at the Euler character, you can look at the Poincare polynomial, which mathematicians can also calculate. And yeah, I'm not quite. You have some ideas what that refinement parameter would be if you want to include it in the U-plane, but yeah, that's also a bit open. Thank you.